Hello and welcome to Uppaal tutorials. In this episode, I would like to show you how to use Uppaal, just basic features and some non-obvious ways of creating models and interacting with the tool. So when you start Uppaal, you see this blank project model opened, which already has one template with one initial location. So besides the obvious, the new document, open document, save document, undo, redo, zooming, for example, I can zoom in some text here, zoom in, zoom out. When you click on the template, you get in the toolbar several tools. So the first one is by default, it's a selection tool, and there's a location tool, branch point tool, edge tool, and the nail tool. So when you select the location tool, it will create locations wherever you click. So even if you click on top, it will create another location. Similarly for other tools, but if you hold your mouse, if you hover above the tool, you will see a tooltip which explains that by using the selection tool, you can actually achieve all of that by just using one tool, provided that you have a middle mouse button. So the middle mouse button sometimes can be achieved by using this, by pushing the scroll button on your mouse. If you don't have a scroll button on Unix systems like Linux, you can achieve the middle button. Sometimes you can configure by clicking the right and left at the same time, left and right mouse button at the same time. If you have a touchpad, it's possible to configure gestures so that, for example, if you tap with 3 fingers, it will emulate the middle button. So this is what I'm using on my laptop. And this is how it works. So if I just do the middle button by 3-finger tapping on the location, it starts drawing an edge. And then I can click the canvas. It will create an edge for me, a nail for me. Another tap creates another nail. And now if I want to complete the edge, I can again middle click on canvas, and here it has completed the edge by creating a new location. I can create another edge exactly the same way, and now when I want to complete, I can just click on the location, and now it actually discovered that okay, it can complete the edge with this location. So I'll just create some small model for ping and pong. So when you double click a location, you get the edit location dialog where you can enter the name and invariant, exponential rate. You can mark this as an initial, make it urgent or committed. So here I will have 2 locations, serving and receiving. So if I tap on a label, I can actually edit the location label directly, and then I can press Control Enter. It will close my dialog. So this saves a lot of time between switching between keyboard and the mouse or touchpad. So if I want to synchronize, I can write ping, and then instead of clicking the OK button, I can just Control Enter, and then it will close the dialog. So I'm sending ping and I'm receiving on pong. And I will call my process ping. So, and now I need another process which can synchronize with it, which will have the same structure. So basically I need a copy of this. So in order to create a copy, we basically visit the document object model tree our process template, and then hold the control key and then click on the template and then drag it. So once we start dragging, you can see that it shows that, okay, this is not acceptable location to drop it. And the acceptable location to drop it is just before templates or after the templates. So if I just drop it here, now I have 2 copies of the template. So maybe I'll just now rename one. And now I remembered that, okay, I need to swap them. So you can actually drag and drop. If you don't hold the control key, it will simply move. So when it moves, you can see that I can reorder my templates. So this is how I can create ping and pong. So now pong has a feature that it actually serves the pong and listens for pings. And it should start with receiving. So I will right click on my location and say, well, this is my initial location now. So now these 2 processes can synchronize. Now, before moving on to simulator, it's very useful to do some syntax checking. So syntax check is available in the tools, and you can see it says it's available by F7. So it's very common that I will use the F7 key. And now you can see there are lots of problems. So at the bottom it says, well, I have this problem, that problem. So it doesn't know what is pong, what is ping. And at the same time, it also highlights where the issue is. So the ping and pong are synchronizations, and they use the channels. So I will just go and declare channel ping and pong. Now I would like to check again, F7, and now it says, well, system is not a template. So this is leftovers from the blank model. And you can see that what is happening, I'm declaring the system which will consist of a process, and that process is being created from a template. But since our processes do not use any arguments, so it's similar like here, so we can actually create a system declaration just directly. So just say, okay, these are the processes that are going to participate. And again, F7. Now we can see there are no issues, and we can move on and try the simulator. So when we change to simulator, it says, well, in the background, the engine has a slightly different, well, it has a slightly different model. It hasn't seen this model that we have created, so it wants to, we want to compile this. So yes. So once I have compiled, you can see there are ping and pong, and they are synchronizing perfectly. So this is on your right-hand side, you can see the state being displayed, and the middle, usually it will show the variable values of that state, and on the left-hand side, you can see the menu with enabled transitions, and at the bottom you can see the trace so far. So I can select, and I can go and back in the trace. On the right hand side, at the bottom, you can see there is alternative display of the same trace, the simulation trace that has been loaded, but in using the message sequence chart syntax. So you can see there are 2 processes, and they start in this serving and receiving state, and then they synchronize. So there is a message going on, and then it changes the state. So this is a nice display when you can actually see the overview of the whole communication. In this simulator, it also has a nice feature. So sometimes when you're debugging, when you get a trace, it's very long trace maybe, you want to see what things are actually has been executed. So we can actually enable the highlighting of which locations and edges they were visited by that trace. So now we have enabled it, and now we can see all the edges and locations are highlighted in blue that were visited. And if we hover just above the location, it will say, well, it has been visited 8 times by the entire trace and 0 times until current position in the trace. And our current position in the trace is somewhere in the beginning, so you can see nothing has been visited. So if I backtrack to the very initial state, nothing has been visited, but when I progress, you can see there is the light blue. So this has been visited in the trace in the beginning before the position, and this blue, is darker blue, has been visited after the current position. So it says 0 times until current position. So this is useful. Could be useful when you want to know which parts of the system has been visited. Once you enable this, there's this another menu item which can show the syntactic coverage. So this is kind of a cumulative coverage diagram. On the x-axis there is steps, and on the y-axis are how many elements have been visited. So my current model is very small, so it does not display much here. So as you can see that all the locations are covered quite quickly. So 2 out of 2 for the ping and 2 out of 2 for the pong. And if we take the total for the system, that's basically 4 locations in total. So it's 4 out of 4. So these are the edge, how many edges were covered by the trace, and this is all elements. So this is basically a sum of locations and edges, and the system shows the sum of all the processes. Right, so besides dragging and dropping, it's possible also to use copy and paste feature. So if I just select something, Control-C, Control-V, and it basically creates a new copy of the stuff. If I select just edge, Control-C, Control-V, it creates the edge, but the edge alone cannot exist without location, so it will also attach the locations. So for timed automata, we want to have some kind of time. So I'll just introduce a clock T, which would stand for the time. And now if I just go to the simulator, you can see that it shows that now we have one variable T, and initially it's, so in our case, it just says, well, the values of T can be anything, but just greater than 0. So when we are taking edges, it actually takes this symbolically. So meaning that it takes the edge for every value of T that is greater or equal than 0. And you can see there is no upper bound, so it can be up to infinity. So this is not very interesting so far, but I could add some constraints. So maybe the serving should happen within 10 time units. So I will add an invariant, so to force the serving of pings to happen within 10 time units, and we don't have time to wait for infinity. And we can serve this ping at least, it should take at least 5 time units to serve a ping. So now we will enforce this, and maybe we should, let's do the same for the pong. So I'll create X must be within 10 time units. And let's serve the pong after 5 time units. So now if we go to the simulator, okay, we have syntax errors, and the syntax error, well, it doesn't know what is X. Well, X is actually a clock, and Pong also needs to have its own separate clock. So when I'm declaring in the local declarations, these are going to be two different clocks. So ping has its own clock and Pong has its own clock, but they both are called X. F7, and now we know what is X. And now let's go to the simulator. And here you can see our T is allowed to, so if I don't select any transitions, again, it says, well, we can delay up to infinity. Well, this is not really true. So the invariant says that we can stay up to 10 time units. And if we select the deadlock, well, it says, well, this stuff does not exist beyond the 10 time units. And if we take a transition, well, it says, well, the transition is available between after 5, and afterwards T can be anywhere. So let's take that transition, and now we see that T can be between 5 and 10, and we just continue. So after a while, you can see that we actually converge, and T cannot move beyond 5 and 10. So that basically the clock, the time is being stopped after 10. And what you are seeing is basically a Zeno behavior. So you can have infinitely many steps within finite amount of time. And that amount of time we have 10. So this is not a good system. So it will basically stutter at time 10. So, and the reason is that when we serve this, we need to specify from which point of time we're actually measuring this time. So this 10 for X is actually measured from the last Pong. So we should reset our X. And when we are doing resets, Uppaal supports both C-like assignments and Pascal-like assignments. So it depends on what do you actually like. So you can actually write colon equals. So this is like a Pascal syntax. And we can also model this reset for Pong, and I will use a different syntax here. So it's better to be consistent, but just for the sake of the example, I'm going to mix. So now we will be able to reset our X. So if I just model now, you can see that now T is free to go to infinity. So this means that the model does not, nobody in the system model does not block the time. The global time is not blocked. So this is a sane, more sane system. And you can see that X, the clock X is changing between 5 and 10, and then it can also even reach 10 and 20. And this is because they can wait in the receiving up to 20 until another process kicks in. Let's just make this a bit more complicated. So suppose Ping is a very good player, and Pong, instead of serving, it may perhaps drop the ball. So I'll create an extra location here. So this is the behavior that this process can actually drop the ball. Now, if I go to the simulator, we can play this, and now we are stuck. So now we can see that Pong is in the location that does not have any outgoing transitions. That's why, so this is stuck. This Pong process is stuck, and if we analyze ping, it is also stuck because it cannot do any, and it does not have any transition to take, because Pong is now cannot be satisfied because Pong is stuck. So when all the processes in the system cannot make an edge transition, then Uppaal calls this as a deadlock. So this is where it declares that, okay, we have a deadlock. There are no transitions available anymore. And I also would like to show that when the Pong is in the serving position, it actually has two transitions available. So this is non-determinism in discrete transitions. So it can choose either one transition or another. In timed automata, there is this also implicit transition time delay. So you can actually see that when I'm selecting the edges, the transitions, it shows that the timings are different. So for different transitions, that the different timings are, so these transitions are valid at different times. So in timed automata, implicitly, there are basically non-determinism between choosing the transitions and another non-determinism for taking a delay transition. So you have to always think about the implicit delay, even though it does not really appear in the simulator. So Uppaal will explore all possibilities. So if we go to verifier and ask, is it possible that there are no deadlocks in the system? So it will explore all possibilities, and well, in this case, it's not satisfied. So it means that there is a deadlock. So we can actually get a trace, and now we can switch to the simulator to see, okay, this is one of the possibilities that the system can be deadlocked. So we have to always think about the delays, and Uppaal will explore all possible behaviors, including the delays. And sometimes students get an impression that, well, I would like the process to move on, do something rather than just staying in the location. So maybe some other process is waiting. So like in this case, okay, the Pong went to drop the ball, and ping is now stuck. It cannot do anything. So maybe we can add a location that if we don't receive ping, Pong, then maybe we should declare that we have won the game. So now let's examine the behavior. So it's always possible for the ping to declare a winning. So even though Pong is maybe still playing, so this is a premature victory. So maybe we should not allow this. So let's allow this only after some time. So let's reset our clock and allow to go here only if we have not received after 20 time units. So here we will restrict so we cannot do the winning unless it did not arrive within some time. So this is a classical timeout functionality. So now, as you can see, as long as Pong is replying, the ping cannot really take the winning transition. And now let's say we will drop the ball. So once we drop the ball, it will be able to take the winning transition. But if we ask the verifier, is it possible for, is it always possible to, for the ping to win? This is not true. So there is some way that it can avoid. So let's examine this trace. So here is a trace which says, well, that it avoids winning. So we can see that it's definitely not in the win position. But this trace, as you can see, it's marked in red. So this means this portion of the trace is being repeated indefinitely. So basically, Uppaal found a way for the system to loop in this, using this sequence of transitions. So the two sequences, they can alternate, and then ping will not be able to reach the winning. So this is a counterexample, the infinite counterexample that's being loaded in a finite trace, and this is how you read it. So the red part is the infinite part. Okay, I think I have covered most of the use cases. There is, if you look at the demo examples, it's possible to create some template. So it's possible to use template parameters. So suppose I would like to have multiple Pong players. So maybe ping is so good that maybe we can pair it with two Pongs. And a common way of doing it, we can actually assign a parameter for Pong, which is a const parameter. So meaning that if it's const and then we put it into the system declarations without filling it, then Uppaal will fill it by itself. So we can actually say, okay, I have a parameter integer from 0 to 2, and its name is just identifier, and F7. So now we have a Pong template which takes an argument, a parameter ID, and it must be an integer between 1 and 2. And as you can see, I'm not satisfying that parameter. So this parameter is going to be satisfied automatically by Uppaal, and it will fill in all possible values for this template. So it's going to use 1 and 2. So it will create Pong 1 and 2. So let's see how it looks like in the simulator. So now in the simulator, you can see there is ping, and there is Pong 1, and there is Pong 2. And now we can play ping pong. So now Pong 2 has dropped the ball, and then ping declared a victory. It is also possible to create partial templates. So another way of doing the same thing, we can actually create another template. So suppose I have a Pong which takes a parameter between 0 and 2. And I'm going to use the Pong template to create another template. So now I have a Pong template. And similarly to what I have shown Pong, I can declare this Pong, and it will fill in all the parameter values, meaning between 1 and 2. So now we are going to have one process for ping, one process for Pong, because Pong does not have any parameters anymore. And I will say we are going to have another bunch of processes called Pong, where the parameters will have to be filled in by Uppaal. So now let's see how it looks like. Okay, not so fast. I need a name right? Even though I'm not using it, I need a name. So now we have a ping and pong. Ping, pong, and pong 1 and pong 2. We can play again until somebody loses the ball. I can actually, so right now they are synchronizing through the channels which are shared. It is possible to create this sharing through the parameters. So suppose I have ping pong here, and then I'm going to say, well, please use the channel ping. So this has to be a reference. So if you don't declare a reference, then it's going to be a separate value. So it could be, that would mean a separate channel, which makes no sense because nobody else can access this. And then I have another pong. Okay, now it says stuff is unknown. So maybe I will do the same for channel ping and channel pong. So now I need, Uppaal doesn't know how to satisfy these parameters. I don't have this. So it says, well, there are 3 process parameters that needs to be satisfied. So I'm going to say that my ping process is going to be created out of the ping template, which uses ping and pong channels. Similarly, my pong process will use the ping and pong channels. So now I need to say I'm going to use this process and that process. F7, everything is good. Now go to simulator, and you can see I have created the same system, and they use the same ping and pong. Now, if I wanted to create multiple processes, I could say again const int 1 2 id. So now I'm going to have multiple of these instances. So sometimes the model can be quite complicated, and maybe I want to have an array of these. So for example, I have 2 channels, and I will use the zeros channel over here and first channel over here. And then we can say that, well, we can actually, so this, in this case, it does not make sense, but we can actually use this identifier to select which channel do we actually want. So this will create a pong, which will use the ID. So maybe I'll just alternate, maybe something like this, from 2. So ID can be from 1 to 2, and this channel has ID uses from 0 to 1. So this is a bit problematic. So I need 1 less. So this is inverted and 1 less. That's a wrong range. What about now? One, 2. Okay, this is too complicated for me to reason. So I'll just start with this. So it's either 1 or 0, and this is going to be the alternative. F7. And let's see what does it create. So now we have ping, which uses 1 channel to send, another channel to receive. And these guys are also alternating. But now you can see the Pong, another Pong is Pong1, is doing a different, synchronizing on different channel. So it basically does not, it participates in the game, but now it looks like it dropped the ball. But if we would not drop the ball, it actually plays together with the ping. So now the teams are turned. So the ping is playing together with Pong1 against the Pong0. So message here is that basically you can create different bindings or different templates arranging with different arrays of channels, and here you can actually index with the parameters which then are being filled in the system. So it's very brief and simple, expressive way of creating many processes. That's it for this episode. I hope you like it, and thank you for your attention.